Hello, today we will do Cambridge A-Level, Further Mathematics, Syllabus Code 9231, Paper 2, Further Pure Maths 2 paper, the May June 2025 series, the variant 1. Okay, we've done question 1 and 2 already, now we'll do question 3, which is a complex binomial expansion. Okay, we are given a binomial expansion of two complex numbers, where z is given as a cosine and a I sine. And okay, so we need to use the Moivre's theorem. If you recall the Moivre's theorem, let's say we have a z power n, which is r e I theta, right? Power n. So that can be expanded to I and theta like that, which is the same as, right? We have the once you expand it to the sine and cosine form, the n goes inside. Sorry, it's cosine first, right? Cosine n theta and I sine n theta. So this is the De Moivre's theorem, basically saying that the n, alright, power n, you can just put it inside to the as a scalar multiple of the angle, or in which case also on if you represent it on the Argand diagram, if you have a power, that also equates to a rotation. I mean an equivalent rotation of some angle. Right, and um okay, so now we have this. First, let's deal with the whatever that's inside. So z minus 1 over z, let's rewrite the reciprocal of z as the power of -1. So z -1, using the De Moivre's theorem, I can write as um, cosine of negative theta, right? Because we write the power as a multiple of the angle inside, add with sine negative theta. Okay, from here, let's do a bit of simplification, because we know that cosine is an even function. Okay, so what means even function is that when we do the Maclaurin's Taylor's series expansion, all the x is a power of even powers. So no matter what angle is inside, even if it's negative, if you have a power of an even number, that will just how to say, we cancel out the negative. So cosine of a negative angle, therefore, is just the same as a positive cosine, right? So there will we rewrite that. Okay, again I say using the expansion, right? Or there's other ways of proving this, but if you have negative theta squared, it's a positive theta. If negative theta power of 4 is a positive theta 4, and so on and so forth. However, for sine negative theta, right? Negative theta, sine is an odd function, meaning that all the powers are odd. So if you have a negative theta power 1, that's a negative theta power 3, that's a negative theta cube, and so on and so forth. Okay, and so this sine a negative theta, what we can do is bring the negative out of the sine function. So we have a negative I sine theta. Okay, so that is a what we call the reciprocal of z. So what we also can do is we rewrite z in its sine and cosine components. So this is the z power 1, then we minus z to the power of -1, then the whole thing with power 5, right? And so the cosine and cosine cancel, we're left with negative, and multiply negative is a positive, so we're left with 2 I sine theta power of 5. Up to now, what we just write as like this was right here, we have this result, and we'll continue to use this later. But now let's try and expand this form, just the z. Okay, the z also 1 over z, or maybe I straight away write it as a z power -1. So I think by now you guys have no issue using the binomial expansion, further maths level at this point, right? And but even so, I'm not sure whether is it in the formula sheet. It is, right? Yeah, it is here. So if you somehow forget it, you can refer. Okay, now that I have finished expanding this binomial series, I have grouped together the both positive and negative exponents which are the same numerical value. Why we're doing this is okay. Let's do the Moivre's theorem again. We know that let's say Zn, okay, is a cosine n theta plus I sine n theta. Okay, we've proven this, or I've shown just now how to prove it. And if we have a negative exponent of the same magnitude, okay, cosine again negative n theta, it just is the same as a positive cosine. And then we have a negative I sine n theta. Okay, from the same result as previously. So Zn minus Z negative n, you get again 2I sine n theta. Okay, so this is true. So if we have 5, 3, and 1, okay, this is Z power 1, right? We can rewrite all of this in this manner. Alright, so Z power 5 minus Z negative 5, you get 2I sine 5 theta. Here we have minus 10 I sine 3 theta. And finally, positive 20 I sine theta. That's it. And yeah, on our right hand side, we have also got this one, 2I sine theta power 5. Okay, power 5. So we have 2 power 5. I to the power of 5 is just I, and then sine to the power of 5 is sine power 5. Yeah, and everything else will remain the same. And since we have not sine, the imaginary number on both sides, I'll go ahead and multiply everything by the imaginary number, which doesn't change anything because everything has the imaginary number, and if it becomes I squared, that's negative 1. So that cancels out everything. So 2 power 5, we can rewrite this entire equation after simplification. And what does the question want us to do with it? Cosecant to the power of 5. Cosecant to the power of 5. Okay, so we remain let's do the sine theta. Will have to divide on both sides, right? We divide by sine to the power of 5 theta, and then we also divide it by this here. And on this side, I'll bring down this entire sine expression onto the bottom here. Okay, since we know 1 over sine power 5 here, that will be the reciprocal of sine. So it'll be a cosecant power of 5. And to simplify further, yeah, let's factorize the 2 outside here. Okay, finally, I think we've made it to the exact same form. So we have A as 16. A is on top, right? B is the coefficient of sine 3 theta, which is negative 5. And C is the coefficient of sine theta, it's 10. So we have the 3 values here. So that's the shown, okay, we've shown it can be written like that, and that will be question 3.